Welcome back. Our previous video went through the Hotz-Miller approach and talked about how having a terminal action in our model can be used to eliminate the recursive nature of our dynamic programming problem. The key idea is that terminal actions have a continuation value of 0, and so they can be used to normalize our model in such a way that we can avoid the backwards recursion problem. But what if we don't have a terminal action in our model? What if our decision makers can make choices indefinitely? Are we out of luck, or can we actually use the CCP methods in this case as well? In today's video, we'll introduce a concept known as renewal actions, which generalizes the set of models through which we can apply the CCP estimation method beyond just models with terminal choices. And the key idea is that a renewal action will reset the state space, and so we can normalize with respect to that action to obtain a cancellation in our future value terms that can undo the recursive structure of our problem. And we'll apply this idea to the Rust bus engine model, which is a model that has this renewal property. Let's start by formalizing the definition of this renewal property. We say that an action is a renewal action if previous choices become irrelevant to the state once I take that renewal action. So in math terms, my state at t plus 2, if I chose renewal action, which is indexed by k, is going to be the same regardless of what choice I made in period t. So our states transition from xt to xt plus 1, depending on the choice that we made in period t. And if I chose j or j prime in period t, I might have different states in xt plus 1. But the idea is that regardless of what the t plus 1 state was, if I choose option k, the renewal action in t plus 1, then I'm going to have the same states in t plus 2, regardless of what I did in period t. So that might be a little bit counterintuitive on the math, but that's the formal definition, and we'll see how it becomes useful in a minute. So option k is going to renew the state space, which just means that if I choose k and t plus 1, then my t plus 2 state is going to be the same regardless of what I chose in period t. And the idea as it relates to conditional choice probabilities is that this renewal property is going to make for a clever normalization to allow me to eliminate the recursion. And this is true even if my choice set does not have a terminal option. And the key idea here is that the normalizations I make don't have to be optimal. And this is something that I really didn't understand for quite a while when I was studying these methods in my doctoral program. It may not be optimal to replace the bus engine in successive periods, but we can still make that normalization. And the fact that we don't really see successive replacement in the data very often exactly shows that it's not a valuable thing to do. So that kind of gives us some intuition for how these CCPs actually would identify these conditional value function differences that we're interested in. So let's do something we did in the prior video, which is normalize our big VT plus 1 to be little VKT plus 1 minus log of PKT plus 1. So again, we went through this in the video just before this. And then we could expand VKT plus 1 to be UK of xt plus 1 plus the continuation value given that I chose k and t plus 1. So I chose j in period t because that's my conditional value function. But then I'm normalizing t plus 1 with respect to option k. So that's going to give me this transition probability here. So if I substitute this into the recursively substitute, I'm going to have that my VJT is a function of my choice in period t plus the future value given that I chose option j in period t plus some additional future value given that I chose j in period t and k in period t plus 1. And then I also have beta times Euler's constant from evaluating the Emax in this period t plus 1. So the only thing I have now, so I have two utilities, one in period t, one in period t plus 1. I have a CCP in period t plus 1, and then I have an ugly future value term in t plus 2. So now let's do the same exercise, but for vj prime t. So let's choose another option, j prime. It doesn't have to be j, it doesn't have to be k, it doesn't have to be 0. And we're going to also normalize that future value term with respect to choice k. So I'm going to do the same exercise. I'm going to say that my j prime, I took action j prime in period t. That's going to give me the flow utility, and then some transition probability in t plus 1. I'm normalizing with respect to k in t plus 1, and then I have a successive transition probability here for my expectation for vt plus 2. So by virtue of this renewal property, these big vt plus 2 terms will cancel out. So if you remember, I had the same exact term here for big vt plus 2 on the previous slide, but I had an fj instead of an fj prime, but everything else was the same. So the renewal property says that these things are the same, whether it's on this slide or the previous slide. And so then I have that little vj minus little vj prime is a function of the differences in the flow utilities plus the differences in the future period utilities of choosing option k minus the log probability of choosing option k. And then I have different transition probabilities on the state space here. So these xt plus 1s will be different values depending on which conditional value function I'm starting at in period t. And so these things won't necessarily cancel out, in part because the f's are different, but even if the f's were the same, the x's might be different in t plus 1, and so those are going to be different numbers. But the point is that we've got this difference conditional value function simply as a function of flow utility parameters and things that I can see in the data that I could estimate in a first stage. So that's the idea of how the renewal property can be used to eliminate the recursive structure. So let's do this in a little bit more detail with the Rust bus engine model from our prior mini-series. We've got two choices and we've got flow payoffs. So if dt is 0, I'm going to pay some maintenance cost that depends on the mileage of the bus and the parameters of my cost function. If I choose to replace, I'm going to get a scrap value difference, and I'm going to pay some replacement cost. So I have some maintenance cost for a brand new engine, and then I have the replacement cost here. So because replacing the engine always sets the state back to 0, because I got a new engine, so no miles traveled on the engine, and that's true regardless of what the odometer reading was before I replaced the engine. So then this means that action 1 is our renewal action. And so in this case, we're only going to need a 1 period ahead replacement probability to capture the future value of making that decision. So how does this work? Let's change our notation to match the infinite horizon problem that Rust was estimating in reality. So we have my future value function for replacing in the current period is the flow utility of replacing plus my big V t plus 1, or my big V in the future is going to be written as V1 minus log of P1. And because I chose replacement in period t, my state is going to be 0 in t plus 1. My engine has 0 miles on it. And then I have Euler's constant times the discount factor. If I choose to maintain the engine in the current period, I'm going to have some utility cost for maintaining it. And then my future value, I can normalize with respect to replacement. So it's going to just be whatever the replacement value was for whatever mileage I accumulated in period t, because I maintained instead of replaced in period t. And then there's some transition probability as well. So here there's no transition probability in the replace line, simply because there's no stochasticity. I had a brand new engine and I chose to replace it again. And so there's no evolution of the state. And then we can note that V1 of x prime is going to actually equal V1 of 0. And this is a special case of the Rust model. So in part, there's the renewal property, but the little V1 is a function of utility and future value. So this renewal property really only applies to the little v, the continuation part. So once I replace, I'm going to have the continuation value be the same, because if I'm always replacing a brand new engine, then I'm always going to have the same continuation value for that engine. But then also the utility specification that Rust gave is basically saying that the utility of replacement is constant in the mileage. So this is kind of a really restrictive assumption that he's making, but he's doing it to simplify the model. So if we go back to his model, basically it's just saying that the replacement cost and the scrap value are going to be equivalent regardless of what the odometer reading was. That might be a valid assumption if the only thing that happens is the engine gets melted and turned into tools or whatever. But maybe the scrap value would be higher if the mileage were lower in reality. In any case, those two assumptions together are going to make it so that regardless of the odometer reading, at the time of replacement, the future value is equivalent. So then we basically have that both the current flow utility portion of V1 and all the future value part of V1 are equivalent regardless of what the odometer reading was when I chose to replace it. So then this simplifies things because we're going to be able to eliminate these V1 terms quite easily, and I'll walk through how that works. We can basically take this V1 here and turn it into a V1 of 0, and then because these transition probabilities always sum to 1, we're effectively integrating over the density of F. So those terms are going to cancel out because I have a multiplication by 1 here. And then that's going to give me my final formula, which is only a function of the differenced flow utilities and the differenced replacement probabilities at the different states. And then here I've combined these the log of P1 terms. But I could have kept this one out because this is not changing with respect to x. This is just a constant. But it's a little bit more compact to put it in this format. So that is what the different conditional value functions look like in the Rust bus engine model once we apply this conditional choice probability estimation approach. So in the end, we just have a simple static logit where we're estimating these terms in the static model, just like we would in a very basic logit model. And then we can get these transition probabilities and the P1 of the different P1 values from our first stage estimation, and then use those to construct an adjustment term that we then use in our static logit model. So the whole point of this video was to show that there's a slightly broader class of models to which we can apply these CCP estimation methods. However, renewal actions are still quite restrictive, albeit slightly less restrictive than terminal actions. And so you might still be wondering, is there even a broader class of models that I can apply these tools to? And the answer to that is yes, and we'll talk about that in the next video. This additional class of models are models that have the finite dependence property, which we'll introduce momentarily. Thanks.